Okay, so today we will discuss about signal distortion in transmission. In the last lecture, we had discussed that the effect of channel through which when a signal has been transmitted from the transmitter side by, let's say, an antenna, radiated from an antenna, it propagates through various kinds of propagation channel. We have studied that in our previous slide. I'll just revisit them. For example, we may have a ground wave radio wave propagation, sky wave radio propagation, line of sight radio propagation. Huh. So as we had discussed before, that this is the channel. Channel introduces distortion, interference, noise. The distortion, the distortion can be taken care of by something known as equalizer filters. The interference can be taken care of by filtering, and the noise is something which we have to deal with in our life. Okay, so let's come back to, yeah. So we'll discuss about signal distortion while transmission. There are two kinds of distortion. One is linear distortion, and the second one is non-linear distortion. So linear distortion is uh, distortion where, for example, if the channel HF, this is the transfer function of the channel being bandpass in nature because we have already modulated the information over a carrier. Channel transfer function, you already know from signal systems what is the transfer function. It is the Fourier transform of the impulse response of the channel. It has an amplitude response and a phase response. So when we say linear distortion, it means that this amplitude and phase response of the channel is not a function of the signal strength itself. So the reflection, refraction, the diffraction, they are not a function of the signal strength. So irrespective of whatever be the signal strength, high or low, you have the same effect. While for the case of nonlinear distortion, when signal propagates through various kinds of nonlinear elements, for example, in the receiver side, after receiving the signal, you may have an antenna with some active circuits. The active circuits, for example, low noise amplifier, mixer, and other things, those are nonlinear in nature. In the transmitter side, the actual signal you have to probably amplify a lot such that you increase your signal strength. However, amplification, large amount of amplification means you are operating in the nonlinear regime. So you have these power amplifiers basically, which are nonlinear in nature. So they introduces something known as nonlinear distortion. Okay, so coming back to linear distortion, let's first understand the linear distortion. We have HF is A e power j phi naught. This is the constant phase, and you have a frequency variation which is e power minus j 2 pi f tg. We'll see what is tg. So this is function of frequency. The amplitude is constant, so it's a flat frequency response. The phase shift, if you see the phase shift, what is the phase shift? Phase shift is phi naught here and minus 2 pi f tg. It's a linear phase shift. Linear phase shift in terms of frequency. And this is a very good channel. A channel which has a flat frequency response and a linear phase shift is something which is desired and is known as distortionless channel. That means the signal is not distorted when it propagates through this channel. Our goal is to have a channel or equalizer. Goal of an equalizer in the receiver is to combine with the effect of the channel and the equalizer, we should be able to have a flat frequency response and a linear phase shift. That is the goal. So what does linear phase shift translate to? Let's see. So the phase shift essentially means delay in time domain. So the time delay TD, we see this is minus 1 by 2 pi f argument angle of HF. So uh, if you substitute this, the angle value here, it is Tg minus phi naught by 2 pi f. That's why it's a function of frequency. If the channel did not have a constant phase shift, so phi naught would have been 0 and henceforth Td would have been equal to Tg. The time delay would have been equal to Tg. Okay, but however there is a constant phase shift and henceforth it becomes a function of frequency. If this constant phase shift was not there, Td would have been constant. Okay. Now let's say consider an input signal, input band pass signal. So we have at a frequency omega c, we may have cosine omega c and sine omega c, two carriers. They are orthogonal to each other. You know orthogonality from signal systems. So at a particular frequency, cosine and sine are orthogonal, definitely. The integration cosine omega ct, sine omega ct dt over the whole time is equal to 0. In other words, the inner product is 0. That's what we mean by orthogonality. So consider this bandpass signal with x1t as the amplitude of omega cosine and x2t as the amplitude corresponding to the sine waveform. And a minus sign is just for notational convenience. So consider this a general expression of a bandpass signal passing through a channel, and the output is denoted by yt. So when it passes through the channel, so we have if we correspondingly you can find out what is ht, and yt can be given as a. The phase shift phi naught comes into picture, so we have cosine omega c and the delay tg. So cosine omega c t minus tg plus phi naught. The envelope x1t is also delayed by t minus x2 delayed by tg, and sine omega ct, the carrier is delayed by omega ct minus tg and the constant phase shift phi naught. Fine. Just try back at home, find out the ht and ht convolved with xt and see if you can obtain this result by t. Very good. So just to bring in this time delay into the picture, so we have a x1 t minus tg cosine. The time delay is tg minus phi naught by 2 pi f. So omega c td is basically omega c tg minus phi naught. So you have omega c tg minus omega c tg plus phi naught. So that means we have a minus td. So this expression boils down to a. The envelope is amplified by a, scaled by a rather. x1 t minus tg, this is the delay of the envelope. The carrier is delayed by t minus td. Similarly here, for the second case, for the sinusoidal carrier case, we have amplitude scaled by a, carrier is sine omega c t minus td delayed by td, envelope x2 t minus tg delayed by tg. You see the significance of tg. Td or time delay is known as carrier delay because you see the carrier is delayed by td, or it is known as phase delay because it's obtained from the phase of the transfer function of the channel. Tg, which we had not defined what is Tg there, you can very easily understand now, is basically delay of the envelope. So it's known as envelope delay, or in physics term known as group delay. So we have two very important concepts in channel linear, the two very important characteristics of linear channel. One is the phase delay, another is the group delay. Now, how is Tg related to the channel transfer function? It is minus 1 by 2 pi del f argument of angle of hf. So, if you take the derivative of the angle, so this is the, if you take the derivative of the angle, derivative of the angle is, we have constant phase. If you take the derivative, that vanishes, and you have 1 by 2 pi, 1 by 2 pi, you have this term, Tg term coming. Okay, so while on the one hand phase delay is just minus 1 by 2 pi f angle of hf, group delay is minus 1 by 2 pi derivative of angle of hf. Very important. Group delay is significantly important than phase delay. Phase delay denotes the delay of the carrier. Carrier finally will demodulate out in the receiver. Our group delay denotes the delay of the envelope, and the envelope contains the information. Remember, x1t and x2t, these two contain the information in the initial bandpass signal. So the delay corresponding to the actual information, this is not an information delay, group delay. Okay. So now you see there are we will try to understand the significance of them by an example, but we'll try to before that we'll try to see that often we confuse between something known as phase delay and phase shift. Constant phase delay means the carrier is delayed by a constant amount that is desired, as we said. It is required for distortionless transmission. Huh? Constant phase shift, it means that the carrier has a constant phase shift of phi naught, let's say, whatever it is. So it causes distortion of signal. We'll see what does that mean. Constant phase shift may appear in various channels. The channel may provide constant phase shift because of the path that it needs to propagate, because of the, or maybe because of the amplifiers which are present. They may give a constant phase shift of 180 degree, or quadrature filters give a phase shift of 90 degree, or so on and so forth. So let's try to understand the significance of constant phase shift. Again, try to remember, distortionless transmission means constant phase delay. As we had discussed here, the transfer function of the channel with flat frequency response and linear phase shift, which is the constant wave, is desired. Okay, let's see this test case. An approximation of a square wave as given by, let's say, for example, by the first three fundamental and the first two harmonics. So we have at a fundamental frequency omega naught, third harmonic 3 omega naught, fifth harmonic 5 omega naught. Of course, the square wave has its odd harmonics in with a duty cycle of 50%. Ideal square wave has, if you do a Fourier series analysis, you'll get its odd harmonics. Very good. So you see, this is the first harmonic, omega naught. We have the second, we have the third harmonic, 3 omega naught, and we have the fifth harmonic, 5 and three harmonics are three sine waves are present. They combine to give kind of square wave. There are oscillations, of course. As you bring in other higher order harmonics, odd harmonics, 7 omega naught, 9 omega naught, and so on and so forth, this slowly gets smoothed. However, there is some glitch at this transition, and that will not go away. That glitch is known as Gibbs phenomenon, or Gibbs shooting, overshooting. And so it's a, because square wave is at the junction, at this transitions, it's a non-differentiable function, and you are approximating by a continuous differentiable nice smooth function. So naturally the combination of all these harmonics would not give ideally a square wave, right? Combination of a differential function or functions won't give you a non-differentiable function at certain points, and henceforth those artifacts come into picture. Okay, so you have probably studied this in signal systems. You may please revisit Open and Wilsky's book to take a look at Gibbs phenomenon. Okay, so you see, we are studying two cases. Low frequency attenuated. So the lower frequency ranges, the channel is such that the lower frequency are attenuated. Attenuated means, for example, when it passes through a channel, let's say these amplitudes are kept same. This is decreased by 25%. This is decreased by 50%. So you see, the square wave will be distorted like this, the linear distortion. Okay, the lower frequency attenuators, we have so you have much more oscillations. Case B, when high frequency is attenuated, so you keep the lower frequency same, higher frequencies are attenuated. Channel is such that, for example, this is attenuated by 25% and this is attenuated by 50%. So you have more lower frequency content, and henceforth compared to the original square wave, you see it has been smoothened out, pretty much smoothened out. Okay. Now, an interesting thing we'll see when it, again consider this signal, when it passes through uh, a constant phase shift. Let's say the same signal, this combination of three sinusoids, it is passing through a constant phase shift of minus 90 degree. So the first sinusoid, omega naught, sorry, this omega naught is shifted by 90 degree. You have this fundamental frequency. The third harmonic, which is 3 omega naught, shifted by 90 degree. The fifth harmonic, which is 5 omega naught, shifted by 90 degree. And henceforth they all start from 0, because it's shifted by 90 degree means cosine becomes sine. Huh? You see, the combination of them now gives you this kind of signal. Huh? Very weird looking signal. Not a triangular, but it's kind of a flat plateau, then a triangle kind of sense. And if you keep on increasing the harmonics, it will slowly peak at this point. Note the amplitude here. The amplitude of the square wave was unity, right? The amplitude of this guy, maximum peak of this guy, is now almost 50% more than the amplitude of the square wave. It's almost 1.5. Huh? The excursion plus 1.5 minus 1.5. Huh? Signal is completely distorted. So you see the effect of constant phase shift. Just with a minus 90 degree example, you see that the signal has been totally distorted. It no more represents a pure square wave. So we will now move on to nonlinear distortion. Okay. We have studied linear distortion. What did we say? Nonlinear distortion is something where the channel characteristics depend on the signal strength itself. So a system having nonlinear elements, for example, the power amplifiers are extremely nonlinear. The antennas with active circuits embedded in it too. You know, we recent days we do some kind of reconfigurable antennas. That means the antennas parameters or the filters, they change with frequency or adapt with the frequency, or in the channel environment, the beam is steered in various directions. So naturally they will have nonlinear elements to control. They will have transistors, they will have several kinds of diodes to control the behavior or reconfigurability. So these are known as nonlinear elements. And the characteristics of a nonlinear elements cannot be described by transfer function. Transfer function is only defined for a linear system, time invariant system. So we use instead something known as transfer characteristics, output and input characteristics. For example, in a diode, you know what is the transfer characteristics? Piecewise linear. So up to 0.7 it's constant, input was there, and then it is linearly increasing. So likewise, you have various kinds of transfer characteristics, input and output. It is now known as transfer function. Okay. So this transfer characteristics yt, we say t as the transfer characteristics of xt. Typically we express in terms of a polynomial expansion. So yt can be written as a1 xt. So if we have only this two, then we have a linear system plus a2 x squared t plus a3 x cube t and so on and so forth. It depends on the higher powers of the signal. If we take the Fourier transform of this, we cannot take the see, input will have a spectrum xt, will have a spectrum xf, output signal will have a spectrum yf. But the system, the nonlinear system, does not have a transfer characteristics, cannot be expressed by Laplace transform. Of course, there are other techniques like Volterra and Wiener Volterra series expansion. So we'll not go into those now. So this is the spectrum, not the transfer function. So the spectrum is given by, if you take the Fourier transform, a1 xf, a2 x squared t. So the Fourier transform of x square t is xf convolved with xf. X cube t Fourier transform is xf convolved with xf convolved with xf. Okay. So what do we understand from here? That if, for example, the signal xf, xt, or and its Fourier transform xf is band limited over a band, xf convolved with xf spreads it to twice that frequency band. The three convolutions spread it to 3 times or more. So that means the output spectrum is no more band limited. Even though the input signal is band limited, the output spectrum spreads over wide frequency bands. This is the first important distinction from linear distortion. In the case of linear distortion, if the input was band limited, the output was limited to the same band. Okay. Now we choose a very special case. The tone xt is cosine omega naught t. So yt, if we calculate from here, if we substitute back here, so yt has a DC component coming from the square and cube, which is a2 by 2 plus 3a4 by 8 and so on and so forth. And we have the omega naught, the fundamental frequency component, which is a1 plus 3a3 by 4 and so on and so forth. And we have cosine 2 omega naught, which is coming from a2 by 2, a4 by 4. So we have taken like 4, the x square, x cube and x4, a4, x4. So if you expand them and collect the corresponding terms for up till, let's say, 2 omega naught t, you arrive at this expression. So we have certain parameters for nonlinear distortion. One of the most important parameters is known as second harmonic distortion, in short form known as SHD. It is the ratio of the second harmonic that is generated, that is basically not required in the system, unwanted signal, second harmonic, compared to the original first harmonic, which is desired. So ratio between these two, a2 by 2 plus a4 by 4 divided by a1 plus a3 by 4. So in a nonlinear system, these are the parameters of interest. Similarly, of third harmonic distortion, let's say you somehow suppress the second harmonic by using certain techniques, that you need to go to the next higher level, which is THD, third harmonic distortion. So we talked of balanced and unbalanced transmission line, or if you have a balanced amplifier or balanced filter, you can somehow suppress these second harmonic, but then third harmonic comes into picture. Okay. There is a certain another the terminology in nonlinear distortion known as intermodulation distortion, or IMD. What is it? Let's say we choose two signals. XT consists of two frequencies, cosine omega 1t and cosine omega 2t. For a linear distortion case, when this will pass through a channel, the output will be A1 cosine omega 1t plus A2 cosine omega 2t. It will only have those two frequencies. But for a nonlinear channel, YT will include, if you bring it here, so omega 1, omega 2, if square of them, you have the product terms. That means you will have cross product terms. Omega 1 plus omega 2, omega 1 minus omega 2. X cube, you will have omega 1 minus 2 omega 2, omega 2 plus 2 omega 1, and so on and so forth. So YT will include all the harmonics of F1, F2 and also the cross product terms between these two frequencies. And henceforth, this is known as intermodulation distortion. You see, between these two, intermodulation, these resulting signals are known as intermodulation products. So intermodulation distortion. We need to characterize how much intermodulation distortion is provided by the nonlinear system. That is also a figure of merit. The third problem which happens in nonlinear distortion is crosstalk. We choose xt, which is x1t plus x2t. The cross product x1t, x2t, if you take the Fourier transform, we have x1f convolved with x2f. So as I mentioned before, even though x1f and x2f are disjoint frequency bands, let's say we have two signals with different frequency bands separated by a guard band where there is no signal. So we would expect that the output should not be, the output frequency band should not be merged, right? They should be also disjoint. However, X1F converted with X2F can overlap with both the bands. Just take a small example. Take two bands, 0 to B, B plus delta to 2B, and then take the convolution of these two bands, and you will see that the convolution can overlap with both the bands. Henceforth, leading to something known as crosstalk. That means the information of the second frequency band passes to the first frequency band and vice versa. This is a very critical problem in a nonlinear distortion. So next lecture, we'll see how to take care of this problem. Thank you.